Welcome and hello. This is a video lesson in the FHWA hydraulic toolbox, specifically using the Riprap calculator. We're going to be talking about culverts and spurs in this lesson. So if you're interested in following along, I've got the user interface up on the screen right here. And the first step is to, first of all, add a Riprap calculator. All right, go up to calculators and then new riprap analysis. Boom, here is the calculator that we're going to be using for this lesson. Specifically, the structure types, that's culvert outlet protection, open bottom culvert protection, as well as spur. I wanted to let you know that the description of this video will contain a few other related videos that are associated with the Riprap calculator, as well as a few links to download some of the associated PDF files that I'll be referencing in this video. And I should also mention that the user's manual itself is available at the help menu. First option down here is the hydraulic toolbox user's manual. Okay, let's go ahead and get started. I'm going to right click Riprap data. And then the first structure type we're going to be looking at here is culvert outlet protection. So go ahead and make that selection from the structure type. Boom, there we go. And what we're doing here is the culvert outlet protection structure type is used to size riprap for dissipating energy and preventing erosion at the downstream end of culverts where high velocity flows exit. If we turn to the user's manual, this is chapter 11.6, starting on page 47, culvert outlet protection. Here's a diagram. Here is the equation right here for the D50 stone size or aggregate size. And then below that, we have the different parameters. But these parameters don't actually provide a whole lot of information. For instance, it doesn't identify which value is for which variable. So for that, we're going to turn to the HEC 14 document right here. If you haven't downloaded this PDF file already, it's available at one of the links in the description of this video. Okay, so if we scroll down to the next page, here is that same equation for D50. It's 0.2 times D, where D is the culvert diameter, and then it's times this product of Q over root GD raised to the 2.5 power, all raised to the 4/3 power, times D over TW. TW is the tailwater depth. D, again, culvert diameter, I already said that. Q is the design flow rate, and G is the acceleration due to gravity, okay? Tailwater is unknown, use 0.4 D. The tailwater should be between 0.4 of the culvert diameter and the culvert diameter. Whenever the flow is supercritical in the culvert diameter is adjusted at using this equation 10.5. All right, just wanted to also mention on the following page, there is an example that starts towards the bottom of the page here. We're not going to be doing this example, but I wanted to point it out because some of the riprap structure types have examples, and I think they're done pretty well here. Okay, so it just shows you the question and then the solution step by step. All right, so let's go back to our riprap calculator. First, what we want to do is select the channel. So we can either create a new channel and then input the specific data right here, or we can use an existing channel by clicking on the existing channel. I already have this channel 1 that's already saved and created in my project. So we'll just go ahead and use channel 1. There's channel 1 right there. And then there's also a button here to transfer values from the channel calculator, but it seems like it does that automatically. Here are the different parameters for that channel. We have a 50 CFS design flow. The channel depth is 2.347 feet, and so on. It's a very modest slope of just 0.2%. And then down below here, we have the input parameters, and even below that is where we're going to see the results. So for the input parameters, let's get started. 50 CFS is our design flow. That's good. That's copied over from the channel data. Then culvert diameter, I'm just going to make something up. I'll say it's a 4-foot diameter culvert. Normal depth of the culvert, 2.347. That's again coming from our channel data. And then after that, we have our tailwater depth. It's supposed to be between 0.4 and 1 of the diameter of the culvert. So I'll just go ahead and say 2 feet. That would be 0.5 times the diameter. And then after that, the flow type is either subcritical or supercritical. I'm pretty sure that it is subcritical just based on the slope. Okay. And then down below here, we have our results. D50 is showing as 87 millimeters. So that's just a few inches. It also says that the specific gravity for this equation here is 2.65. All right. So with that small diameter, of course, this is class 1 riprap. We can also see some of the dimensions here for the apron length, thickness, and apron width at the end of the apron. What I like to do in these lessons is tweak the input parameters and see how that changes the D50 value and the riprap class. So let's go ahead and do that real quick. I'm going to change the culvert diameter from 4 feet down to 3 feet and see what happens. So 4 feet is now 3 feet. And if we scroll down, now the D50 value is 128 millimeters. So that's still pretty small. It's about 5 inches. Let's try to get it up to class 2 because it's still class 1. Let's increase the flow from 50 to 100. So I'll just come up here to input parameter flow, and then I'll just overwrite 50 with 100, tab. And now we're up to class 4 now. That requires a D50 of 323 millimeters. So it's a much larger rock that's being used to dissipate that energy. All right. So that's how the culvert outlet protection structure type is used within the riprap calculator or riprap analysis. The next structure type we're going to work on is open bottom culvert protection, which is right here. Sometimes culverts are not circular or box shape, but rather an arch shape. So there's no actual culvert material on the bottom side of the culvert. It's just using the native riverbed material. So in that situation, we'll get a picture of that up in the screen in just a moment. In fact, let's do that now. So what we're looking at is the user's manual, page 48 and 49 here. Open bottom culvert protection. Here's the user's manual on the bottom of page 48 or 47 and the top of page 48. And then here is the equation for D50. And then again, there's no description or a variable listing in this parameter list. So what we're going to do is go to the hydraulic engineering circular number 23. That's this document here, the PDF, also linked for your download in the description of this video. This is where it starts on page 351, riprap protection for bottomless culverts. But if we scroll down to page 355, and then here is that same equation for riprap size. The variables are shown here. So K sub R is the sizing coefficient, either 0.38 or 0.68 based on the lab best fit or the design curve that envelops the lab data, which is recommended. Also Y sub 0, that is the depth, I believe, average flow depth. And then S sub G, that is the specific gravity of the riprap. VAC, that's the average velocity of the flow at the culvert entrance. And what are we missing? G is the acceleration due to gravity. I promised you a picture, so wait 1 second. Here we go. Figure 18.1. This is on the bottom of page 351. This is a bottomless culvert example. Kind of looks like a bridge, to be honest, but lots of different culvert sizes are available in the arch shape. I have a whole separate playlist of videos covering the high 8 culvert design. The open bottom culvert protection structure type is used to size riprap for protecting the stream bed beneath and downstream of open bottom culverts from erosion and scour caused by concentrated flows. All right, so let's head over to our calculator finally. What I'm going to use is our channel data once again, just channel 1. So all of the channel parameters are set and ready to go. After that, we have our input parameters and then finally our results. So for the input parameters here, the design curve that I'm going to use is this one right here. It's recommended, envelops the lab data. That means that this K sub R variable is going to be using 0.68 in our equation. That's either that or 0.38, but we're going to go with 0.68. Okay. Next up is our average velocity at the culvert entrance, 2.508. That's simply flow divided by area. So our flow is 50 CFS, and then the flow area is 19.93. Average flow depth, also based on our channel data, 2.374. That's, of course, based on the flow rate and the geometry. And then invert elevation. This is something I'm just going to randomly make up. We'll say 150 feet. And then contraction scour plus long-term degradation. That is sort of two things we're adding together. The contraction scour is the lowering of the stream bed that occurs when the flow area is reduced. We'll say that's 1 foot. And then long-term degradation is the gradual lowering of the stream bed over time due to watershed scale processes. We'll go ahead and say that's 1 foot as well. So we'll just say this term right here is a total of 2 feet. Okay, so when I tabbed off, we now have our results. I'll scroll down. The D50, based on our input data, is 129 millimeters. That's a little bit below the 165 for this class 1, so it uses class 1. 129 millimeters is about 5.1 inches, so less than 6, fairly small. And then the layout parameters are also shown here. I don't mention this for all the structures, but probably should. So we have a few different lengths like 10 feet, 20 feet, 20.5 inches, 60 inches, or 5 feet. So what these values are here refer to how the riprap should be set up along this open bottom culvert. So if we go to the HEC 23 document, specifically figures 18.9 and 18.10. That should be on this page right here. All right, so the length, this is figure 18.9. The length would be upstream and downstream of the culvert. And then figure 18.10 shows some of those other lengths. We have the W sub T, W sub B, and Y total, which are our values for these three values right here, the last 3 rows in this layout section, this layout table. Let's go ahead and make one modification to see if we can require a higher class or a higher D50 size for a riprap for this open bottom culvert. What I like to do is just increase the flow rate. So let's change it from 50 CFS to 100 CFS, calculate, okay. It recalculates, and now the D50 is 187 millimeters, 188 millimeters. That's about 7.4 inches. So we need to upgrade to class 2 type riprap. All right, so that's it for open bottom culvert protection. The last structure type I wanted to cover in this lesson was spurs, channel spurs. Again, I'm going to use channel 1. Let's switch this back to 50 CFS, calculate, and OK. And let's see what the user's manual has to say about this on page 45. Here we go. Channel spurs. The spur structure type is used to size riprap for protecting spur dikes and groins that project into the channel to redirect flow, reduce erosion, and stabilize banks. So right here we have the direction of flow down through the river, and then here is a channel spur right here. We don't want this to erode, so we need to add riprap. Here is the equation right here. D30 is what we're calculating apparently, and then we've got all these terms. This is the correct equation, but again, we don't have any idea of what these terms are necessarily without referencing the hydraulic engineering circular number 23 on page 74. So let's go there. 74. Okay, cool. So here is that equation. We have D30 equals this term right here. Y is the local depth of flow. S sub F is the safety factor. C sub S is the stability coefficient. So if we're using angular rock, it's 0.3. If we're using rounded rock, it's 0.375. C sub V, that is the velocity distribution coefficient. As you can read here, it's 1 for straight channels or inside the bends, 1.25 at the end of the dike or downstream from the from concrete channels, and then it uses this equation here for the outside of the bends. C sub T, that's the blanket thickness, we'll just use 1.0. And then this term right here, we've got the design velocity in the numerator. K1, that's the slope correction factor based on the bank angle. The bank angle is something else we're going to be inputting. We'll get to the actual calculator in just a moment. Specific gravity, depth again, and gravitational acceleration. Okay, let's check out the calculator. I'm going to scroll down a little bit. For flow depth at the end of the spurs, for channel type, our options here are natural channel or trapezoidal channel. We'll just go with natural channel. Flow depth, that's the same 2.34 that we've been using before. That's coming from our channel calculator. The riprap shape, either angular or rounded. We'll go with angular, and because we selected angular, the stability coefficient is 0.3. Blanket thickness coefficient of 1, we're just going to use 1. We said that. Velocity distribution coefficient 1.25. So this would be like for the end of the dikes or downstream of concrete channels. This really refers to the location around the channel dike itself. Channel cross-sectional velocity. So this is again from the channel data. Centerline radius of curvature of the channel bend. All right, so let's just make something up here. I'll say it is 500 feet. Okay. And then width of water surface at the upstream end of the channel. This right here is again 11.694. That's coming from the top width of my channel data, 11.694. And then bank angle. So right now it's 1 to 1. So that makes a 45-degree angle. If I change this to a larger number, such as 4 to 1 would result in a lower bank angle. And what we remember that the bank angle affects this K1 term. The K1 is in the denominator. So I'm not going to try to figure that out, but I know where to reference it if I need to dig into it more in the future. Specific gravity is 2.65, and then the safety factor, we'll just go with 1.1. All right, so with all of this data, we have our results down below. What I'm interested in here is that D30 is 49.3 millimeters, D50 is 59 millimeters, so really just a couple inches. Class 1 is fine, probably a low probability of erosion based on this data. So let's go ahead and mix it up and try to get a little bit larger riprap requirement. Instead of a centerline radius of 500 feet, I'm going to change that to 200 feet. And then instead of a safety factor of 1.1, I'm going to change that to, how about a 2? So boom, tab. All right, so scrolling down to the results, now we have a D30 of 113 and a D50 of 136. That's in millimeters, still class 1. Let's reduce the radius one more time to 100. Okay, cool. So now we're up to class 2, a little bit larger rock size right there. That is how to use the Riprap calculator specifically for channel spurs, culvert outlet protection, and open bottom culvert protection.